Okay, hello everyone. So we finished the alternating series with the conditional convergence. So let's just take review on the absolute and the conditional convergences. I think I would just go here, just go for a couple questions and we can move to another questions. So here we have questions on the absolutely convergent, conditionally convergent, and all, or perhaps the divergence series. So you have number 22 to 33. Or 34. So we could pick some of them. Let's choose. I think we can start from the simple one. Maybe 24. And maybe 29. And how about 32? Okay. So let's try these three numbers. Okay, these three numbers. 24, 29, 32. So this is because it's clear and obvious that this is going to ask whether it is absolute convergence or conditional convergence, and some of them actually you can see some of them has this terms, which is the -1 with power of n or n plus 1 or n minus 1, which means that we are still in the alternating series, right? We are still in alternating series. Now, what should you do to check? The first thing you need to do. What you should do first. So you have a lot of series here, but the first step should be the same. What is it? What's this first step? You can have at least two requirements. Remember, in alternating series, you only have two requirements to check. First is what? Anyone still remember? Only two. The idea, like it seems like a lot, but there's only two things. What is it?
Remember?
That's the method, but the idea is not that. We only have two. First, in alternating series, we need to check whether the functions decrease or not. Second, the limit should be equal to 0. Okay. And for the absolute or conditional convergence, we take the absolute value. We take the absolute value. So basically, we ignore the -1. We ignore the negative. We only take this. For example, if we have this -1 here, okay, we only see this. Take the limit. Take the limit. If the limit is not 0, then none. Is this 0 or not? Is this limit 0? Yeah. So we could conclude right away. No need for other method. Okay. So I'm going to write here just to make sure. So first steps, take absolute value. For the series, let me write like that, or maybe like that. And then the second one, take limit I think there's a few steps that it should work for all of you. So take absolute value. So which means that we are going to take the limit of this. So take the limit. So let me write here. So we can take the limit. And we can write as 1 plus 1 over n squared, which means this is equal 1. So it is clear it doesn't show up as 0. So let me write here that this is not 0, right? The second thing, and we can write that limit. This also doesn't exist. Or you can just write directly. You can write directly that by divergence test, the series diverges. So I don't think this is needed. Okay, we can just write this along. Okay, now if we check the 29, okay, we have trigonometric expression, the sign. So let's say we have let me write sum 1 plus 2 sine n over n cubed. Okay, now we have trigonometric expressions. So what should we do for this one? The same thing. We take the absolute value. We take the absolute value, which means that every sign that we have, there will be no negative forms, right? So it will always positive. So the maximum this expression can be, the sign will be 1, right? Okay. So the sign is 1, the maximum. Then the maximum or the possibility for this numerator will be 3. So we can make some sort of comparison. Okay. So that's your cue or some clue for your strategy. Sometimes for some complicated forms, and then it involves trigonometric expression, maybe you need to check with the comparison, and make you can make the absolute value, because sometimes sign can be a negative, and it can be negative, and for sure this will be alternating. This will be alternating because of the signs. Right? So we could start with taking the expression. Let me write here. We can take the expressions and take the absolute value for the AN. Okay, and then we say that this will be less than 3 over n cubed. And of course, this should be also, it should be positive, right? It should be greater than 0. So for n start from n equal 1 and greater 1, then this will for obvious reasons this should work, right? And then of course from this 3 over n cubed, we know from the P series, right? We can also conclude that since 1 over n cubed, this will be convergent, is convergent. And then our series is less than the P series. So we could say that we can write first. So here's the logic. Let me write the logic first. But in the exam, you can write just the conclusions. Okay. But this is how, if you put this into a machine, this the logic that should work. Okay. So this will be that. So this works as take the absolute first. So this will be a converges by the direct comparison test. So because the absolute of that series is converges, then as conclusion, the series is we can write absolutely convergent. And to be precise, if you want to write really complete, so series is convergent. Okay. This is the logic. The logic. Well, in the exam, you could just write the last term. That's okay for me. But if this is machine, this is how it works. You try to see the absolute value. Okay, the absolute value works for this one, which means that, okay, since this is convergent, this should be convergent. And because this absolute value converges, then we can say that the series here is absolutely convergent. And that is why the series is convergent. This is like looping words by words, but that's how actually, if we put in some algorithm, that's how it works. So I'm not sure like whether you think, because if you learn math, if you learn like engineering or how to code, you learn how to write something systematically, like from the first process, the second process, and third process. And when you learn like calculus or maybe even later engineering of mathematics, it's not how you compute and get the answer, but how you process that, how you work from the first analysis, take it deeper, and then you can make a conclusion. That's how it works. So we are learning pattern and logic. We are learning pattern and logic, and it will work for all. I think this will be helpful for you. So if you learn, like usually in undergraduate, the analytical skills is not that much. But if you are preparing very well, it will be sufficiently needed in your, for example, if you need for master degree, or if you want to maybe increase your skills more, take some certifications, learn some software. All the basics in the undergraduate courses, although it's like really a lot, and sometimes you feel like, why I need to learn this? You will see that when you learn calculus, you learn math, you learn how to process in your brain systematically. That's the, I think, the ideal works. Okay? So if you think that there's too many formula, blah, 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 then you are not processing all the systems correctly. So you need to either find a way to learn, like which are preferable methods. There are many ways. I think you could just go browsing YouTube for those trainings, like how to learn. So learn how to learn. It's actually works. Some of them maybe works for you. Because I actually try to find a way and then try to like imagine like a frogs. If you have a like in your kitchen, you boil a water, and imagine like you put the frogs inside the water. Maybe the frogs feels okay, it feels cozy, but then the temperature increase. What the frogs will do is will start jumping. So you need to challenge yourself. If you are not challenge yourself, and if you think like, oh, you see the words, oh, I understand. But you need to challenge your understanding. Do I understand what I wrote? That's how you take your own self to challenge, and you know your limit. Okay, you know your limit, and when you know your limit, you know how to overcome your problem. Okay, so I think if you are still struggling, like learning mathematics or all the basic stuff, if you are not solving this right away, in the second year, maybe you can still survive, but later on, it will be a burden. It will be a really big problem, because the only way that you can be safe is yourself. So not your TA, not your professor, but yourself. Your skills is the one are attached in you, within you. So if you don't understand yourself, then that's actually the problem. Okay, so I hope you found your way. You found your way how to learn, how to study. Okay. Anyway, let's continue this part. Okay, I think the interesting one is the 32 here. So I given the first one diverge, right? The first one diverge. This one diverge. This is absolutely convergent. And let's try number 32. So we can try the absolute value first, and then try to compute. Or if you remember the alternating series, we only have two requirements. The series should be decreased. The limit is 0. If we see this, and let's take some numbers, and since this is 3, but it has a square root, so it must be like 3/2, which the top one is only 1. So this 1 is greater and greater, which means that if we increase the n from 1 to 2, it will be decreased. Agree? Right? Agree? Because this is 1, the top is 1, the bottom, the maximum is 3/2, right? The dominant n. So which means that it should be greater in the denominator. So in fractions, if the bottom is greater and greater, it will be smaller, right? It will be smaller and smaller. Okay, so it's decreasing. We take the n larger, take the limit. This is probably 1 over something, because this is the greatest, the dominant one. So it should be something over n. This will be 0, right? Okay, yeah. So it's converged based on alternating series. But the question is asking the absolute convergent or conditional convergent, which means to take the absolute and then check whether it's going to diverge or converge. If it is diverge, then this is conditional convergent. Okay. If still converge, then it's absolutely convergent. Okay. So there's one argument first. Okay, so argument number 1. Let me write here. Let me write the question again here. So this will be the question. N and then N. So let me write the first argument. Let me write argument 1. By alternating series. This is greater than I'm just changing the n with n plus 1 just to show you that the next terms is less. Okay. And then limit okay. So by alternating series is convergent. Okay. If the question is asking diverge or converge, you can write convergent. But the question need to specify conditional or absolute. So we take the check the absolute or conditional. So we take the absolute. So let's take the AN as this. So this is argument 2. Okay, argument 2. So we take this as our okay, and then take Bn as 1 over square root of n. So we are going to check so we are going to use the limit comparison test. Maybe to make it precise, this is decreasing for n start from 2. Okay. From 1 is still not true, but it will work for n equal to. So we take the limit. Let me remove this. Okay. So we take so take the limit a over bn. So let's write this. Multiply with square root of n, or this can be written and we can get this, the n and the n half, right? Or let me write this as n with power of half. So you see that this will be 3 over 2, which means that this is the same as this, right? Okay. So this we could write in a big square root n cubed over n cubed plus 2. And we could definitely see that this is going to equal 1. Okay. And then since or maybe right, since the Bn, or the series for 1 over square root of n is diverges, right? Due to P series, because P is less than 1, then the final result, the series of the an, which is n over square root n cubed plus 2, also diverges. But the alternating series is converged. So this is conditional convergence. Okay. The final result is let me make this smaller. Okay, so I hope you can see the argument. Okay, the argument. So first, two requirements for alternating series. The series decreasing, the limit is 0. We know converge, diverge. But the converge, it can be absolute convergence, it can be conditional convergence. So the second argument, you take the absolute value and then check this series. It can be using the divergence test, it can be the comparison test, okay, or maybe the integral test. Any test that we have done before. Then if you know Like if it is diverged, it will be conditional. If it is converged, it's absolutely convergent. So it can be done for the full argument, but if you want to make a shortcut, to make it like quicker, you can just take the absolute value and then see whether it's converged or diverged. Okay. If it is converged, you can directly absolute convergent because it must be. Okay. If you take absolute value, if it's converged, then it must be absolutely convergent. But if diverged, then you check the alternate series. If the alternate series, check the limit. If 0 decreasing, oh, it's converged. But it's diverged here. Oh, it's conditional convergent. Right. So the logarithm or the algorithm will be faster if you check the absolute value first, and then determine the alternate series if it is converged. So to make it easy, check absolute value, diverge, converge. This must be absolute convergent. Check alternating series. Okay. Okay, this must be true. This must be true. But of course, if you want to show all the logic, then you can start like taking one by one, checking the alternate series if you want to make it a full argument. Okay, the next, I think I will keep the exercise and you can check the exercise by yourself, or maybe I will add later, especially near the midterm. We'll give more exercise. There is one more method, and then we can review our strategy. So one more method, and this method I consider as the most convenient method to check. Okay, because when you know how, and then you see the pattern, and you will see that, oh, this should be using this test, and it will be, I think, quite fast. Okay, perhaps any questions first? Any questions? No? Okay. Okay. Okay, let's move to the next page, which we are going to start what we call the ratio test, or we have two actually, but they are going to be they have similarity, so they are in the one subtopic, ratio and root test. So we start by look at the ratio test, okay? And why it's called the ratio? Because we are treat them as ratio in geometric series. So there are three statements. We are going to take the limit of so from the series, we take this sequence an, and then we are comparing the next term and the previous term, the an plus 1 and an. So basically, we have an, maybe n squared, blah, blah, blah. So we are going to compare that in the ratio system like this. So comparing this, and it will result in some finite number, which it can be less than 1, greater 1, or equal 1. If this is less, then it will be absolutely convergent. If it is greater 1, this will be divergent. If it is equal 1, then we need to check with other method. So it's inconclusive. And it works like the previous absolutely convergent works. So we take the absolute value. So it's actually using some statement from the alternating series, which you can just take the absolute value and then check the result. So basically, it's, I think, going ahead compared with the previous alternating series. Okay. So you could directly compare the an plus 1 with an. And if this is less 1, then you can go for absolutely convergent. Okay. So you could have done like, so it can be combined with the alternating series. So you could just check with ratio tests, and then if this is absolute convergent, and then you can just stop, and then you don't need to check the alternate series. So the idea, okay, for this, let me just explain a little bit more, just for proving how it works. So it's basically coming from the geometric series. Okay. So we take the L, okay, as the result of the ratio. So we take the limit. And we choose number R from the ratio such that the L is less than R is less than 1. Okay. So eventually the ratio will be less than R, and we say there will be some integer, we define the capital N to define the terms. Okay, so we say that an plus 1 over an, this will be less R when the terms is greater or more than the integer capital N. Or we can rewrite this equivalently So we see that it seems we are going to see it's more and more like a geometric series. And if we take more and more arguments, like if we take the n, increasing the n, you will see that we are going to have and let's say this is the n, capital N. And then we take the n plus 2. And if we take the n, or maybe just 2 should be enough. And so in general, that the an plus k will be less than an r with power of k, for k is at least 1 or greater 1. And we now have, let me write here, in terms k, we have an multiplied with r with power of k, which means that this is going to be the series that is, if we break down the series, this will be pretty similar to a geometric series. Let me, I think I make it too big. Let me make it smaller. So this will, by arguments from this statement, this will converges because it is a geometric series with r between 0 and 1. So by the inequality that we have, then this series is or also convergent. And vice versa for the other arguments, that is the L is greater than R, greater than 1, then there will be divergence, okay, based on the same reasons for the geometric series. This is just the argument that if we increase the n by changing with the integer +1, +2, +3, +4, it will be adding more and more in line, which is going to be pretty similar to the geometric series. And we have now from this we build a new series, okay, a new series like that. Then we say that this will converges this should be n capital, sorry, should be n capital. Maybe let me write here. Put n equal n. Okay, maybe this is some example. I just take it from the textbook. So this is a really quick example. So basically, what we need to do for the ratio test is just taking the an plus 1 over an. Okay. So this an is this. An is n cubed with 3 over power of n. And you will see some pattern later on. Okay, we are going to have a break. Okay, we will continue later. Okay, let's continue. So I think this ratio test, since this is, I think, quite important, and this will also can be done for the next subtopics, which is the power series. We are going to see how the ratio test works, and basically what you need is a little bit algebra for solving the ratio. So for example, here we have the an plus 1 divided by an. So basically we start taking all the substitute all the n. So n plus 1 cubed over 3 with power of n plus 1, right? That's for an plus 1. Okay. Got it right. And I will ignore the negative 1 with power of n, because that is going to be absolute, so we can ignore that. And let me write this 3 with power of n over n cubed. Okay. Okay. So this is actually coming from here, n cubed 3 with power of n, and we move this. Okay. And basically, we are going to simplify this. And I will write n plus 1 cube. Or let me just combine these two. Cube. And then 3 power of n is the same with that, right? So we can cancel. So we can cancel this with that. So we have 1 over 3. So let me put 1 over 3 in the front. Okay. And then what should we do next is we take the limit. Okay. So take the limit. So we can write the limit maybe here. Take the limit. This would be 1 plus 1 over n, and then cube. So this will be just 1, right? So we have 1 over 3, which is less than 1. So by ratio test, series is absolutely convergent. Or you can say, therefore it's convergent. So whenever you see power, either n with power of something or some constant with power of the variables n, then perhaps you should try the ratio test, because it is, I think, one of the most easiest method to check. So we have the divergence test, which is super easy. We have this. Okay. Compare with the comparison test, which you need to think what series you need to compare, right? You need to think first what series you need to think. But here, you can just think, rewrite this n plus 1 and n, take the ratio, and then take the limit. If limit is less than 1, it's convergent. If greater 1, divergent. If equal 1, then that's problem. You need to check another method. Okay. So if you see something like that series or something like this, then we need to check the ratio test. And see that we can work with the factorials as well. Okay. Okay, if we see the number 2, example 2, we have n with power of n over n factorial. Now n factorial, it's going to be n multiplied with n minus 1, n minus 2, etc. That's n factorial, right? Okay. If we have n plus 1 factorial, we are going to have n plus 1, and then n minus 1, or we can write n plus 1 multiply with n factorial, right? For n plus 1 factorial. And this is what we are going to use. And you will see this a lot if we are considering the factorials property. So, as usual, we take the n plus 1 divided by n, right, absolute value. And this will be n plus 1 with power of n plus 1, right? Divide, we're still in n plus 1, so n plus 1 factorial, multiply n factorial, divide with n with power of n. Okay. The n plus 1 with power of n plus 1, this will be n plus 1 multiply with n plus 1 power of n, right? Okay. And the n plus 1 factorial is basically n plus 1 multiply with n factorial. So we can cancel the n plus 1 and n factorial, which we are going to have so we take the limit of this n plus 1 over n with power of n. Or so what is this? This is, in calculus 1, we've learned this, that this is going to be the definition of E, right? So this will be equal to E. Okay. Or it will be equal to E as n getting infinity. And since E is greater 1, then the series is divergent. by ratio test. This is if we are using the ratio test. But actually, if you just take some time to analyze, if we are using the divergence test by taking some numbers of the n, then we are going to see that it will be diverged. If we could see, like for example, taking the an is n with power of n over n factorial. So this will be n multiplied with n until n times, and then the n factorial will be 1 multiplied by 2 multiplied by 3 until some n. You will see that for n starting from 1, of course the top equation will be larger. So this will be, we can say this will be greater or equal n. So an does not equal or doesn't approach 0. This is another way. So by divergence test, series is divergent. So whenever you see any fractions with power and or having any factorials, then perhaps you directly you could try the ratio test, because it's very simple. As long as you can solve the algebra for the ratio and you get the final result, and you can conclude whether it's converged or diverged. Okay. But if it is equal 1, then that's another problem. Okay. Okay. Similarly, we can use similar approach with the root test, which I will show you here. Or maybe if you want to write this first. Or let me write with the other example. So the root test is pretty much similar statements. So we are going to have the L as the final result. When L less than 1, greater 1, or equal 1, that's the three possibilities. So So the idea for the root task is basically we have the an, and then we are going to square by the power of n. Okay. So we take the square or the root by power of n for the an. So for obvious reasons, the an, since it is going to have the root with power of n, whenever you see any an that you can somehow find that the an could have a power of n, then you could use this. Okay? So basically, the root will cancel the power on the an. Okay? So whenever you see that, then you can just directly using the root task, and then finding its limit, and then we have three statements when it's converged, diverged, or inconclusive. Okay? Now we could start with this example 4, and obviously you can see that the an has the power of n, which we can take the root for power of n, and then we can take the limit and we can conclude the final result. So whenever you see any power with the nth power, then this we can say that the an, since the an is this, then the usage of root task will be helpful. So we take the square or the root with power of n, which results in 2n plus 3, 3n plus 2. And if we would like to divide all by 1 over n, we have 2 plus 3 over n, and then 3 plus 2 over n. And we take the limit. Oh, let me write the limit in the front here. So we take the limit, which results in 2 over 3, right? And since it's less than 1, then this will be, so series is absolutely convergent by root task. And see the example 5. Mm-hmm. We see that n over n plus 1, but with power of n. So we could take the root with power n, which we have n over n plus 1. It seems that this will equal to 1, which is inconclusive. But if we use but let me write but since we have the n plus 1 with power of n, we can write this as 1 over n plus 1 over n with power of n. And since this is 1 plus 1 over n, this is 1 over e. Okay. The same as the previous page that I mentioned. So as n getting infinity, then the an will get to 1 over e. And since the an by the limit, so since limit, or let me write limit of an is not 0, then series is diverge or divergent by a divergence test. Okay, maybe the last part for today's class will be exercise for the ratio and root test. So hopefully, and since this is going to be correlate with the next subtopics, I hope you are going to get more familiarized with the ratio test. So I will write here, this is inconclusive, but we can take the divergence test. Just an overview before we take some exercise. So basically, we have at least eight tests for the whole convergence, divergence, how to determine the series. So overview, let me write overview. I will write simply from the very simplified test, which is the divergence test. So as long as the limit is not 0 or limit doesn't exist, then we know the divergent. Okay, we know that it's divergent. The second and the third will be the P series. Let me write the P series here. And the geometric series. Okay, I hope you know P series and geometric series. So as long as the P series, for example, you can start the P series by taking 1 over n and 1 over n squared. 1 over n should be diverged, 1 over n squared, and if we increase the terms in n squared, cubed, fourth, that should be converged, okay, from the P series. And then geometric series. Geometric series, as long as we know the ratio is less than 1, then it will be converged. Okay? Or if this is greater 1, then it will be diverged. Okay? So these two are the one that we can usually use for the comparison. So if you want to compare something, You can think P series or geometric series to compare. So that's why number 4 is comparison test. You can have direct, or you can have limit comparison. Direct comparison, usually it's much more straightforward and you can get direct result. But for somehow, if you cannot prove the inequality, maybe difficult to prove, then you can try the limit comparison. Okay. But both of this, you need at least 2 or 3, P series and geometric series, to compare the series. Okay. Okay. So with 1, 2, 3, 4. Okay, we have 5. We have 5, which is the alternating series, which we usually requires series or the b n plus 1 is less than bn, and the limit of the an is 0. Okay. Remember the alternating series, most of the case or frequently you will see that it has the -1 terms, in this in the formulation. Or if you expand, it will be having a plus minus or negative plus negative. Okay. And then as long as you have this, then you can say it's converged. Okay. But remember, in alternate series, we can also have, for the converge, it could be absolute or conditional. And number 6, we have ratio and root. So this is, I believe, 1, 2, 3, 4 is, or 1, 2, 3 is quite easy to see. 4, whenever you see any complicated, like in the fractions, but it feels complicated, then you can try the comparison. Okay. And 5, you see any -1 term that make it alternating, or any terms that makes alternate, then you can check the alternate series. Number 6, then you can check the ratio. Sometimes it is also, for example, you can try number 1, and then you can directly go for number 5 or 6. Depends on the case. Okay. Number 2 and 3 is more like additional reference. Like maybe you can skip this because this is needed, especially for number 4. Right? So you can skip to 5 or 6. Okay, 5 or 6. So if you see any factorials or exponent, you can check the ratio. Okay, ratio test. Or if you see for the roots, if you see n power, you can check the root. Okay. The last one is integral. So it is because it's not really convenient, because you need to do the improper integral. So it will be the last choice. But if you familiar with the integration, and when you see the series and you can imagine, oh, this is the function that easy to be integrated, then you can check the integral. Or if your calculator can do improper integral, that will be better. Can you do improper integral in your calculator? Take the infinity or no? Need to number, right? Need to be number, right? Okay. Yeah, that's too bad.
So we did have an integrated test.
Not sure. You can check. If that is the case, then it's good for you.
No. If we have
Yeah, of course. But I need your argument. the entanglement is helping you to convince yourself, like, oh, I'm correct. Okay, this is all about the testing the series. Okay? Okay, maybe some exercise for ratio test because we haven't started the test exercise for ratio. So let's start taking these two type of questions. So the left one is the ratio. The right one is supposed to be a root. And from this exercise, I hope you can see some patterns here. And for a quick glance, or quick impression for this all the series, you see that it has factorials, or it has the power that is quite large. It has factorials, or it is in this expansion form, but it's still factorials, or in the odd number. Factorials again, and most of that will be large power or factorials or some constant with power of n. Why? Because if the factorials of the power, it takes ratio with its n plus 1, we are going to see some cancellation that it will be, I think, quite often it will appear, and it will simplify our process. And that is the expectation. So that is what you are going to expect. So when you start to write some problems or do some exercise, before you start doing something, you need to have some strategy. So do not come to war without any preparation. Or maybe when you play a game, you go to a dungeon, your level is not enough, and your boss or your the enemy will, I will be kicked out of the dungeon. Okay. Your level need to be at least similar, right? Similar. So when you see this, you need to have like a same expectation. Oh, I expect to get this. So you know, like you have the, oh, this is what I expect. And when you try to compute, maybe something wrong. Either human error, or maybe your method is wrong. Right? Your method is wrong. So you need to verify. That's how exercise should be. Okay. So when you take the exercise, it's not only, oh, I got the number. Okay, I got the number. No. You need to verify your process, verify your results. Okay? You will get better if you know which one is your mistake, and you know how to prepare them. Okay? So that's how to at least improve your learning. Okay, maybe let's start with maybe this, okay, number 9, and which number from the left one, the ratio? Maybe we skip for now. But the ratio first. I will start with number 9, and the other number. Any requests? Any request? Maybe something that is interesting. So maybe let's start with number 9 first. Okay, number 9 first. So since we know that this is going to be works with ratio test, and since this is exercise in ratio test, then we can using that ratio to be work. So we can take the an over an plus 1. Oh, an plus 1 over an, sorry. Okay, right here. So I will write directly. So 10 with power of n, I will write so I will write here, an plus 1 over an, okay? So this will be an plus 1, will be 10 with power of n plus 1. Okay, so we have n plus 1 on the bottom, so we have n plus 1 plus 1, so n plus 2, okay? And then 4. And this is, I think, students make mistake a lot. 2n plus 1, we need to write 2n plus 1 plus 1. So why I know students get mistake, because usually I give this in the exam. Okay. Oh, forget to multiply the an will be n plus 1 for 2n plus 1 and over 10 with power of n. Okay. Now we solve the algebra first. So this will be 10 and 10. This is n plus 2. Oh, it's gone. Okay. This is 4, 2, n. 2 plus 1, so 3, so plus 3. Okay. And then this will be n plus 1 for 2n plus 1 so I will cancel this 10 with power of power n, and then for this one I will cancel, but this is actually, this is 4 2n 4 cube, and this is 4 2n 4. So I will cancel the 4 2n, right, and 4. So this is 4 squared. So now we have 10 over 4 squared, or 16, right? And then take the limit for the n plus 1 and plus 2, which is going to be equal 1, right? So we have, this is going to be 5 over 8, which is less than 1, and we know that this will be absolutely convergent by ratio test. Okay. For some expansions like this, it means that you need to rewrite the series, and then do that, and then find the L less than 1, greater 1, or equal 1. Okay, I think since now is almost 3, and I have a small feedback as usual, just to check. So I hope we can start that in a moment. So the rest, I hope you can try. I think next week we are going to have another overview with more generalized, like the whole testing series, okay, for at least in the Tuesday. Maybe in 1 hour class I will try to review and have like exercise. Like the question will be random, then we need to check like which method should we use.